Hello everyone. Today we're going to start on 2.3 Matrix Algebra. The basic concept here is just simply try to talk about now that we know what a matrix is there some way to actually do algebra with it? Meaning basically doing operations and dealing with it like you would with normal numbers. So we call that a matrix is simply just a rectangular array of numbers. So if you're given two matrices, is there a way to combine them together? So the first operation that we're going to define is matrix addition. So given two matrices, let's say matrix A and matrix B. Let's say the dimensions are the same. Let's say n by m matrix. And let's say we define matrix C to be equal to the sum of A and B. Then C is defined by the following. In such a way that every entry in C, every C sub ij, which is equal to A sub ij plus B sub ij. So what does that mean? Well, it simply means the following. Let's say if A is, let's say A11, A12, to A1M. Let's say A21, A22, to A2M, and all the way down to AN1, AN2, to ANM. And let's say this is A. Let's say now similarly I have B, B11, B12, to B1M. And then B21, B22, to B2M, and all the way to BN1, BN2, to BNM. Then C equal to A plus B, which is equal to A11 plus B11, A12 plus B12, to A1M plus B1. Keep on trying to write I. B1M, and then this pattern continue to AN1 plus BN1, to AN2 plus BN2, to ANM plus BNM. So basically what does it mean? It basically simply mean that when you add two matrices together, you have to add the corresponding number together. And because of that, very important to understand, matrix addition is a binary operation because it combines two matrices together into one. And it requires two matrices to have the same dimension in order for it to work. So therefore, it's impossible to add two matrices with different dimensions together. It's not defined that way. If you try to do that, it will be an invalid operation. And also notice the output of the matrix addition is another matrix that's n by m. So therefore, important to notice is that matrix addition is close. It has closure property. And it is important because it will allow us to repeatedly adding multiple matrices together as long as they all have the same dimension. Okay. Next operation is scalar multiplication of matrix, or matrix scalar multiplication. So let's say given an n by m matrix A, and a scalar, let's say R, if B equal to R times A, then every, B sub ij is just equal to R times A sub ij. So essentially saying that if A is equal to A11, A12, to A1m, and let's say this is equal to AN1, AN2, to ANM, then B equal to RA would just simply equal to RA11, RA1, RA12, to RA1M, and this pattern continue to RAN1, RAN2, to RANM. Very simple. Basically meaning that when you have a scalar multiplication of a matrix, you simply just distribute. Now, also important to notice is that the resulting matrix B is also n by m. So therefore, matrix scalar multiplication is also closed. And this is important because now with both of these, I can now define something called linear combination of matrices. And if some of you having a little deja vu on this whole discussion, you should, because the same exact thing we talk about in chapter 1.1, when we first learned about vectors. Okay, the only difference here is that instead of looking at a vector, which is either horizontal or vertical list of numbers, we are basically looking at a rectangular array of numbers. But the idea is exactly the same. We define the two same exact operation. In this case, matrix addition is mirror the definition of vector addition, and matrix scalar multiplication mirror vector scalar multiplication. So the next thing I want to show you is linear combination of matrices. So a matrix is a linear combination of a set of matrices if this is true, if it is the sum of multiples of those matrices. So here, the linear combination definition is exactly the same as the linear combination definition for vectors. You're basically using multiple vectors as like kind of building blocks with different numbers of them combined together to form a larger or different matrix. So give you a very simple example. Example 1. Suppose I let A equal to, let's say, 1, 2, 1, negative 1, 1, 0, and B, which is 1, 3, negative 5. Oops. Okay, maybe I should write a little space out. 1, 3, negative 5, 0, 2, 2. So notice that both of these are 2 by 3 matrices, and we expect the linear combination to be another 2 by 3 matrix because both sum and multiple define vector addition and scalar multiplication, which we know that both of those operations are closed. So therefore, it's impossible for us to actually get a matrix of a different dimension from this when I combine these two matrices together. Okay, so now I can say if, let's say, matrix C is equal to 3A minus 2B, find matrix C. So it's pretty simple. C will equal to 3A minus 2B. So remember, one way to interpret this is to interpret as 3 times matrix A plus -2 times matrix B. So that way we now have a matrix addition, but have a negative multiple matrix B. So what will happen to that? So simple. So when you multiply 3 by matrix A, you can simply just multiply every single one of the numbers inside matrix A by 3. So it becomes 3, 6, 3, -3, 3, 0. Plus, same thing with B, we'll multiply by the -2, so it becomes -2, -6, +10, 0, -4, -4. And now all I have to do is just simply add them together by adding corresponding number together. 3 plus -2 is 1. 6 plus -6 is 0. 3 plus 10 is 13. -3 plus 0 is -3. 3 plus -4 is -1. 0 plus -4 is -4. So this is what matrix C is. As we expected, matrix C is a 2 by 3 matrix, just like A and B. Pretty simple. Is that any different than doing linear combinations of vectors? No, but you just do more of them. And also the way the solution is also arranged differently. I mean, I could easily say, if I write the same exact problem, but say vector A equal to 1, 2, 1, -1, 1, 0 in R6, and vector B equal to 1, 3, -5, 0, 2, 2 in R6, then I can ask you to form the same exact linear combination. And then your answer will be 1, 0, 13, -3, -1, -4 in R6. But in here, in matrix form, we just arrange them in a slightly different order. One interesting thing I do want to point out is that matrix multiplication, a scalar multiplication of a matrix is a little different than scalar multiplication of vectors. In scalar multiplication of vector, we can interpret that multiplying a vector by a scalar would keep the direction the same but stretches out the length. And therefore, it makes sense that you can now interpret doing non-integer multiple of a vector. You just basically changing the length to some non-integer numbers. Like if I do 1.5 times a vector, it's just stretching out the length of the vector to 1.5 of what it originally was, but keeping the direction of the vector the same. The problem with matrix scalar multiplication is that it doesn't have such a nice interpretation. So therefore, we're just going to keep it as simple as mathematically. You just multiply a matrix or all its element by the scalar. But there's no geometric interpretation of like stretching out the matrix or things like that. So therefore, it's lacking this interpretation. But we can still do it mathematically or algebraically. Understand that scalar multiplication is just simply distributing the scalar into the matrix. Now, one key difference between matrices and vector is that we don't have a true multiplication between two vectors. I mean, we do have dot products, but if you think about it, dot product allow us to form a scalar, not a vector out of it. And we do have cross product that does form a vector by combining two vectors together, but it's only a construct in R3. We don't have a true multiplication between two vectors that will give us a vector that cannot do what we think multiplication would do. Matrices, on the other hand, we do have an operation called matrix multiplication. And it actually created similar to the multiplication that we define for matrix and a vector. So let's define a matrix multiplication for you. Let's say given two matrices, let's say A and B. Now here's the interesting thing. Let's say A is a N by P matrix. And let's say B is a P by M matrix. Off the top of your we just stay right here, you already know the following things. That these are things that you have to learn to pay attention when we define operations and procedure. Okay? That's how you learn and progress into better math student and be able to understand higher level math. Is to learn to now pay attention to things that you normally don't pay attention before because it's not relevant before, but now it is. Here, as soon as I put this down, you already know the following things about matrix multiplication. Number one, it's a binary operation because it requires two matrices to combine to form an outcome. Just like matrix addition, but not the same as scalar multiplication. Scalar multiplication is just a regular operation, not binary, because it doesn't require two matrices to work, just one. Second, notice that the dimension of A and B are actually not the same. Very different compared to like matrix addition, which requires us to combine two matrices that have the same exact dimension. As a matter of fact, the operation matrix addition is invalid when you try to combine two matrices of different dimension. Matrix multiplication, very different. It actually requires two matrices to have somewhat a unique dimension in order for it to work. Okay? Now, also one thing I do want to point out is right here, is A being an N by P matrix, while B being a P by M matrix. Notice the letter P being used twice because of the fact that these two numbers must be the same. Now, I'll go through that more when we look at an example. Next, let's try to define what is the product between these two matrices. Then, the product, let's say matrix C, which is equal to A times B, is defined by the following. Is defined so that each entry, so each entry inside C will be defined as C sub ij, is the dot product between the ith row of A with the jth column of B. So this is very specific in the way that they define matrix multiplication. First of all, matrix multiplication is defined through a whole bunch of dot products. And whenever you're doing dot product, you need to know what two things you're doing the dot product of. Is the rows of A and the columns of B combined together. Okay, very important. Now, it might be hard to understand how that works, so how about we do a very simple example right next to it. Let's say we're given these two matrices, A, which is 1, 3, 3, 0, 2, 1, and B, which is 1, 1, 0, 2, negative 3, 4. I'm going to go ahead and ask you to find A times B. Okay, and how about we give this a name? We're going to say, maybe we'll do this, make it easier. I'm going to ask you to find C, which is equal to A times B. So how do we do that? So, well, let's go and do this. So C would equal to A times B. So I'm going to go and put down A, B. So here's the first thing the student get a little confused. Like, wait, these two matrices are not the same dimension. How are we going to do this? Well, as a matter of fact, matrix multiplication does require them to not be the same dimension. That's the important part. But it does require the following. If I look at the matrix, the first matrix, this matrix is a 2 by 3 matrix. While this one is a 3 by 2 matrix. Here's the important concept. When you multiply two matrices together, when you write out the dimension, these two numbers must be the same in order for the matrix multiplication to be defined. If these two numbers are not the same, the multiplication is invalid. It does not work. Okay, very important. Now, if the two inside numbers play an important role in defining whether this operation is valid or not, they have to be the same for the operation to be valid. What do these two numbers actually represent? These two numbers basically represent the dimension of the product. Meaning in this case, our matrix C is going to be a 2 by 2 matrix. Now, as soon as you put that down, you also realize something very important about matrix multiplication. Matrix multiplication is not closed. Okay, which kind of makes sense because we already know using two different matrices, dimensions matrices, to work together to form this multiplication to begin with. So therefore, there's really no closure to speak of, because unlike matrix addition, where we have to use two of the same dimension and then form a solution that is of the same dimension, here we don't even start with two matrices of the same dimension to begin with. Okay, so therefore make sure you understand matrix multiplication is not closed. Now comes the question, how do I form this product? Well, simple. Do what the definition tells you to do. So if I think about it, matrix C is going to be a 2 by 2 matrix. So I'm going to go and start from the front here. Nope, I do kind of need to see two matrices. Okay, maybe I do this. There you go. So therefore, since C is a 2 by 2 matrix, I can say C is basically C11, C12, C21, C22. And based on that definition, each entry inside C is a dot product of the ith row and the j columns. Ith row of A, j column of B. Or in this case, read A as the first matrix, B as the second matrix. Don't get too tied down on A and B because, you know, I could name the two matrices U and V, P and Q, M and N, or any name I choose. So here's the row of the first matrix and column of the second matrix. That's the important part. So C11 would be the dot product between the first row of A. So the first row of A is 1, 3, 3. Dot product, the first columns of B, which is 1, 0, -3. Notice that those two vectors have the same numbers in it. The same number of elements in it. They're both in R3. And that's a requirement for dot product to be valid. And if you think about it, it makes sense now why the second number in the dimension of the first matrix, which is the column, must match with the number of row in the second matrix. Because the number of row in the second matrix determines how many numbers in a column. And the number of column in the first matrix determine how many numbers in a row. And if those two are not the same, when you write them as vector and try to do the dot product would not be defined. Now I can go ahead and finish up the other thing. So C12 would be the first row, dot product, the second column. And then C21 would be the second row, dot product, the first column. And then the second row, dot product, the second column. So now I have a 2 by 2 matrix, which have 4 numbers inside. Each number is a dot product between two vectors in R3. Now I just simply do the dot product. So it'll be 1 plus 0 minus 9 for the first number. This one will be 1 plus 6 plus 8. Plus 12, I'm sorry. The bottom one, this one, would be 0 plus 0 plus -3, or minus 3 if you want. Then will be 0 plus 4 plus 4. So it seemed to me that it come out to be -8, 19, -3, 8. That must be the products. And the product is a 2 by 2 matrix. Alright? Good. Now here's something also very interesting I want to point out. What if now I ask you to find this? Notice that when I do this, it becomes a major difference between matrix C, because D is now equal to B times A, while B is a 3 by 2 matrix, while A is a 2 by 3 matrix. Notice these two numbers are still the same. And these two numbers now define the dimension of D. Seems to me that D is a 3 by 3 matrix. And this automatically tell you one thing very important about matrix multiplication, something definitely worth writing down. So before we establish that matrix multiplication is not closed, which makes sense. This establishes a second important property about D. About matrix multiplication. Matrix multiplication is not commutative. Matrix D is a 3 by 3 matrix, which by definition cannot be the same as a 2 by 2 matrix, which is matrix C. In order for two matrices C to be exactly the same or to be equivalent or equal, they have to have the same dimensions and all the elements have to be exactly the same. So in here, it showed that matrix multiplication is not commutative. Very important to make sure you understand. So now what I want you to do is this. I'm going to go and state the answer for the product between these two matrices. Okay, let's see if I just write it out first. C is, B is 1, 1, 0, 2, negative 3, 4, times A, which is 1, 3, 3, 0, 2, 1. And then we have a 3 by 3 matrix that would equal to what this is. So I'm going to ask you to kind of pause the video, go and do the problem, and then come back and see the answers, okay? All right, so here you go. I have the answer to the multiplication. I do believe I did it right, but of course, if I make a mistake, please let me know. It's not uncommon for me to make a mistake also. All right, so notice that this is definitely a different matrix compared to matrix C. So therefore, it tells us that when you talk about matrix multiplication, you have to really pay attention to the multiplication and the order that you're defining them. Because if you don't pay attention to that, you will screw up your math. Because sometimes the operation is not defined when you define it backward. And even if you define it backward and it gives you the same exact dimension of the matrix, it still could possibly give you a different matrix. So keep that in mind. The next thing I want to show you is this, is properties. Properties of matrix algebra. So there are quite a few properties I want to show you. Most of these are very basic that you already probably expect or suspect that will be true. Let's say we have three matrices. Let's say A, B, and C be three matrices. And let's say we have R be a scalar. Now notice one thing I did not specify about these three matrices, A, B, and C, will be the dimension. We assumed whatever their dimension would be whatever it is, such that the operation defined in the property would be true. So if I define, let's say in the property I say A times B, I'm assuming that matrix A and matrix B would have whatever dimension it is, so that A times B would be properly defined. Okay, so therefore I don't have to specify what their dimension is, so they could be whatever needed. So the first one is the distributive property, which states the following. If you have A plus B multiplied by matrix C, that becomes AC plus BC. Sometimes this is called the right-hand distributive property because you basically distribute the matrix C from the right into the sum. Now, why do I specify that? Because you could also have a left-hand side distributive property, which would be CA plus CB. Note, CA plus CB does not always equal AC plus AC because of the lack of commutative properties. Okay, which is the reason why the distributive property have to be stated in both directions. Okay, you can actually distribute both ways. Just have to make sure to maintain the order of the multiplication involved. 2. If you do R times matrix AB, that is the same thing as R times A multiplied by B, or same thing as A times RB. So this is an associative properties that allow me to move a scalar multiplication into wherever I want to multiply first, either the product or individual matrices. 4. A times BC would actually equal to AB times C, which also can just simply write it without any of the parentheses. Okay? That is associative property for matrix multiplication, which means that if you can actually define three matrices multiplied together with their dimension properly defined, then you can multiply any two of them first, then to the third one. Okay? Now, however, note the following. You cannot reverse the order of the multiplication. That is not always true. Okay? You cannot multiply them out of order. The order that's given to you has to be the way it is. To define property 5, I do need to define a special matrix, which is called the zero matrix. The zero matrix is just a matrix with nothing but zeros in it. So it plays the role of the zero vector. Okay, and what does the zero matrix do? If I take any matrix plus the zero matrix, I just get A. That's the identity property. Or if you take a matrix and you do a negative of the matrix, they also combine and cancel each other out. That's called additive inverse. And to define property 7, I will define let I be the identity matrix. So you already know what the identity matrix is. So I will have to be a square matrix that would have this property. Oh, sorry, this is a 1. And what does the identity matrix do? Property 7. If you take a matrix A, multiply by identity matrix, it just gives you back A. And interesting thing about it is, it's the same thing as if you take the identity and multiply by A. So in this case, the identity matrix does follow the community properties, where if you reverse the order to multiply the identity matrix, you actually do get the same result, and that would be the matrix that you start with. Now, I know the video is already past 30 minutes, but I do have one last thing I want to show you, and after that, that would be the end of this video. So hopefully it's not going to be too long. Okay, but that would conclude 2.3. The last thing I want to show you is called matrix polynomials. As the name suggests, a matrix polynomial is basically in this form: a polynomial of a variable x is in the form of a sub 0 plus a1x plus a2x squared plus ... plus a sub n x to the n. Example of that would be something like this: a polynomial so that would be an example of a polynomial in the variable x. In this scenario right here, this one is my number a sub 0, which is 1. A sub 1 is 3. A sub 2 is -5. And a sub 3 would be the number 1 in front. The subscript matches the exponents, which is how you identify the proper a value. Okay? The question is, can I form a polynomial just like this using matrices? The problem with that is, in order to do that, I have to define what does it mean when I raise a matrix to a power. So let's define what that is. For a square matrix, this is interesting because for a square matrix, matrix multiplication actually does have closure. Does have closure property. Therefore, it allows us to define what we call the powers of a square matrix. So suppose we have a matrix A. Let's say we let A be a square matrix. It doesn't matter what the dimension it is, as long as it's square. We can define the following. What we call powers of A. So what would they be? First, if I take A raised to 0 power, that just gives us the identity matrix. If I take matrix A and multiply to raise to first power, that's just equal to A. If I A to second power, that's A times A. A to the third power would be A times A times A, or think of it as A times A squared, or A squared times A. And this pattern continue on to A to nth power, will just become A times A times A n times, or A times A to n minus 1 power, or A to n minus 1 power times A. Now with the power of A defined, I can now actually evaluate a polynomial function using this concept. So, example, let's say we have a function f of x, which is equal to x squared plus 3x minus 2. What I'm going to ask you to do is to find f of A with matrix A equal to, let's say, 1, 2, 3, 4. Now, this is the last example, so bear with me here. I know this video is kind of long already. So what do is simply just do exactly what the problem asks you to do. I'm going to do f of matrix A, which basically meaning is 1, 2, 3, 4, raise the second power, plus 3 times 1, 2, 3, 4, minus 2. Now here come the important part, so pay attention. Notice that what I have here in the beginning is 1, 2, 3, 4, raise the second power. Since a 2 by 2 matrix, when I raise the second power, I will also get a 2 by 2 matrix. 3 times 1, 2, 3, 4 would be also a 2 by 2 matrix. The problem here is what happened to the number 2. That is not something that can combine with a matrix, because that is a scalar. So this is what you need to remember to do. What you need to remember to do is the following. In the function f, when it say x squared plus 3x minus 2, it also indicates is minus 2 to the 0 power and 3 times x to the first power. With that being said, that means in here, in your expression, when you plug in a, you're actually doing 3 times 1, 2, 3, 4 to the first power minus 2 times 1, 2, 3, 4 to the 0 power. That is something you have to remember, otherwise you screw up your math. And now all you have to do is simply evaluate now. So this just become 1, 2, 3, 4, multiplied by 1, 2, 3, 4. The 3 get distributed into the matrix. And now what happened to 1, 2, 3, 4 to 0 power? That formed the identity matrix. And now just a matter of find out what this is. So this would be 1 times 1 plus 2 times 3, that would be 7. 1 times 2 plus 2 times 4, that would be 10. 3 times 1 plus 4 times 3 would be 15. 3 times 2 plus 4 times 4 is 22. Plus 3, 6, 9, 12. Minus 2, 0, 0, 2. Notice the output come out to be a 2 by 2 matrix. 7 plus 3 minus 2 is 8. 10 plus 6 minus 0 is 16. 15 plus 9 is 24. And 22 plus 12 minus 2 is 32. All right. Unfortunately, I might run out of time, so during class, maybe we'll do a few more examples. I apologize for this video being long because I do want to finish it in one video so that we can move on to the next section on tomorrow's video. All right, I'll talk to you guys later. Bye-bye.